In this video, we're given the specs on an RLC circuit, and then we're asked a bunch of standard questions about it. So here's our RLC circuit. I see an inductor, a capacitor, and a resistor, and I have an oscilloscope across the resistor, and this is being used as a probe for measuring the current in the circuit, very similar to a lab that we've done. And I'm asked first for the resonant frequency, so this is just a matter of quoting the formula. That's 1 over 2 pi root LC. 8.2 microhenries, that's 8.2 times 10 to the negative 6. For the inductance, 10 microfarads, so 10 times 10 to the negative 6, which is 10 to the negative 5th. And when I run the numbers on this, I get 17,576 hertz. I'm going to write this as 17.6 kilohertz. In part B, I'm asked for the total impedance if we apply a signal at the resonant frequency. And I'll post a link back to where this was first introduced, but the impedance is given by this formula, square root of r squared plus chi L minus chi C quantity squared. And that chi L is called the inductive reactance, and the chi C is called the capacitive reactance. Well, the resonant frequency occurs at the point where this term is equal to 0. So we have a special frequency that makes the inductive and capacitive reactances equal to each other. That term cancels out, and the impedance reduces to the simple resistance for the circuit. So this is kind of just a concept question, because you can just read it right off the diagram. The impedance is going to be 10 ohms. Right when we drive this thing at 17.6 kilohertz. And that is the minimum possible impedance. It will maximize the current in the circuit. To look at what happens at other frequencies, I picked a frequency of 10 kilohertz for questions C, D, and E. And we're going to look at the inductive reactance, capacitive reactance, and total impedance when we're rather far from the resonant frequency. So just to remind you of these formulas, the inductive reactance, that's the effective resistance of an inductor, and that gets bigger when the frequency gets bigger because the induced back EMF in the inductor gets larger if we start changing the current faster. So at 10,000 hertz, that's 2 pi times 10,000 times our inductance, which was 8.2 times 10 to the negative 6 henries. And this gives me 0.515 ohms. Then to get capacitive reactance, that's 1 over 2 pi f times the capacitance. And the lower the frequency is, the bigger the capacitive reactance, because the capacitor can start to have a rather large voltage induced on it by charge building up. So f is in the denominator, and this gets bigger when f is smaller. And I get 1 over 2 pi times the frequency, 10,000 hertz, times the capacitance, 10 microfarads, 10 times 10 to the negative 6, well, that's just 10 to the negative 5th farads. And I get 1.59 ohms for the capacitive reactance. Now I get my total impedance using the impedance formula. And my resistance was 10 ohms. And my inductive reactance was 0.515 ohms minus my capacitive reactance. So these are out of balance now because we're not at the resonant frequency. And rounding to 3 sig figs, I get a total impedance of 10.1 ohms. So just a little bit bigger than it was at the resonant frequency. I didn't ask these questions here, but that larger total impedance means the total current will be a little bit less when you apply Ohm's law. Like the peak current will be my signal voltage over the impedance, and the bigger the impedance gets, the smaller the current gets. And that current will be maximized when we run this thing at the resonant frequency. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.